the right data in the right place. So, you might start off with kind of regional and global topography with tens to hundreds of meters per pixel. So I showed the SRTM, which is one of our big go-to data sets. You might see, like this is, and also Aster has a big global data set, but we're not really getting finer than sort of 10 meters per pixel. There's a really good data system called the GMRT. It's the Global Multi-Resolution Topography and Bathymetry data set. And you can get it from this Marine Geoscience data system, but it's really nice to see both on and offshore data. It's kind of the best available regional data. We start to see widespread moderate resolution, sort of 5 meters per pixel-ish, stereo photogrammetry from space led by polar geospatial people. So these are guys at the University of Minnesota, and they're really big on using like digital globes. So the data you might see in Google Earth, stereo, to produce digital elevation models of polar environments. That's what they're funded to do, to kind of look at melting ice mostly and other changes in the polar region. But they did produce some nice data for the Nepal area after the earthquake there, but it was still only about 5 meters per pixel, so maybe not quite fine enough for some of the applications we have, although pretty good. So this is really where we're interested in this workshop, and this is a really cool figure that Ed built, just kind of show, here's a fault zone of interest, here's our airborne laser scanning along the fault zone, here's that terrestrial laser scanner blasting the fault scars, and then here's our airborne, sort of low-altitude airborne platform balloon or a drone, where we might do structures from motion. So that's where we'll spend pretty much all the time henceforth. And there's a really good paper in the reading from Johnson et al. From one of Ed's students that sort of where you can find this figure in other places. Okay, so I'm just going to show. I'm going to spend some time on this scale thing. I'm just going to feed on it for a while, but hopefully you'll get the point. So this is an application actually from Gayatri and I. We went to Java 2 years ago, and we taught some courses. So there's some interesting, lectures of all sorts on active faults, paleoseismology, geochronology that he and I built that are on this website. But one thing is we went into the field, and there's a fault right behind this little valley called the Lembang Fault, and they had LiDAR data for it. And so this is an important application because here in Java you can see there's a lot of anthropogenic just change to the Earth's surface. A lot of people live there. There's also a lot of vegetation. And so this is a place where the LiDAR can be quite valuable because we can do this classification. We maybe can pull away the vegetation and pull away the buildings. And so let's see. So here's just what the terrain looks like. This is a kind of an uphill facing scarp. So we're looking downhill, and this fault has some kind of normal oblique motion. So you can see the scarp, but what to do with it is quite challenging because it's sort of a low slip rate fault in a pretty heavily altered environment. So here's just one site. You see really a lot of change to the landscape due to agriculture. But then let's watch this video. So here's SRTM 90-meter data. You see the Lembang Fault in here. So it's kind of coarse. You can look along the fault zone in this 3D view. This is ArcScene. Now I put that was 90 meters. This is 30-meter data. So now available SRTM. So starting to get a finer representation of features. Now I'm zooming into 1 meter per pixel Google Earth data. So I got pretty good imagery representation, but still on the 30-meter topography. Now I'm on the 1 meter digital surface model from the LiDAR. So surface means the top of anything. So topography, buildings, or trees. Now, so I can see a lot. It's really pretty impressive, but pretty dense. Now let's see there. Now now we're just getting the digital terrain model. So just the bare earth. I'm kind of going between the two of them. And so now finally we've stripped things off enough that we might be able to start to go after some of these questions of, is this a right lateral offset, and what's the landscape evolution of these channels as they cross this fault zone? But this is kind of a pretty typical sequence of work where you go from sort of regional topography at those tens of meters per pixel down to your finest scale, and then kind of this interaction through 3D in a 3D environment. So any questions?
Did you choose a filter to get from the 90 meter to the 30 meter SRT?
No, they were separate data sets.
Separate data sets?
Yeah. Okay. And you'll see now in open topography we have those data available to download. So are you going to talk about, okay, so I'm going to skip through LiDAR just in the interest of time.
Can I ask a quick question?
Yeah.
When you do the surface mapping versus the one, do you see a difference between the products?
You mean like terrestrial laser scanner
Yeah,
versus?
it seems like you get shadowing if you're doing it from the ground.
Oh yeah, it's yeah. So what Andrew's asking is this question. I'll just come back here. So you're saying what's the difference between data products like this and this one, or data acquisition? Yeah, it's a big difference because of the view direction. So you know the sort of nearly vertical viewing we get, especially for relatively flat terrain, we get good representation. If there's a lot of overhangs, it can be problematic. Here, we can see things if they're facing the scanner well, but otherwise do a lot of shadowing. Chris will talk some about this, but you might have multiple setups kind of around the target area.
For topographic mapping, it actually turns out that TLS is actually a pretty bad tool, because just for the reason you're talking about, because you're close to the ground surface you're trying to map, so you're scanning at a very oblique angle, and oftentimes, unless you're in like even in a Mojave or something, there's always stuff on the ground that gets in the way, whether it's brush or vegetation or rocks, or blades of grass. So the airborne look angles for topographic mapping are actually really advantageous. Yeah, I'll talk more about that.
Good question. So I'm going to jump through some of this technology. I'll just say that this little movie down here, this is a piece of the Tahoe data that we'll play with after lunch. But Chris will kind of go through this. He can say better than me. So just a little bit of a kind of coming into this a figure of Ed made, but you know because most of us are interested in Southern California, sometimes I forget to remind myself about the value of the LiDAR for seeing through vegetation. But some of you are not working there. But here's just a couple examples of these would be the digital surface models. So these are everything. So we've made a digital elevation model out of the vegetation returns as well as the ground. And so you kind of think, well, I guess there's a fault there, right? And so this is Slovenia. This is an early paper, 2005. Here's Tahoe, Sierra frontal fault. Here's Denali. But when we take away the vegetation, the digital terrain model, you start to really be able to take out the fault scarps. And so great value for studying faulting. So open topography, Chris will review, but you know, it's a sort of a portal to high-resolution topography, data, tools, and knowledge. That's something very possible.
I know that mostly we are interested in Southern California. Also, you know, we have very big offsets around here. What is your experience with like all the normal faults that there is in Italy or Greece? It's the method successful in the same way to give us something more?
Yeah, it's actually, you know, there were many students who applied to come to our workshop who are working on the Wasatch Fault, but we didn't admit them because we didn't have room, but we may do another course later. So there's a lot of work on the Wasatch Fault. There's and some nice LiDAR data. There's also some nice work being done in Italy in some of the Apennine normal fault systems. Some nice papers around L'Aquila trying to do some reconstruction of landscaping. The problem is that it's still, this approach works when the displacements are on the order of a meter or larger. So if you have small earthquakes, any sense of motion, you have a harder time taking the signal out. And that's a kind of a data challenge. You know, we can fly the planes lower and get higher shot densities, maybe do better airborne. Maybe we need to get on the ground, or we need to do drone-based structure from motion to try to push the sampling scale down to pick the finer scale up. But that's sampling, and then there's also uncertainty. And so some of the uncertainties in the positions also are limiting our ability to do different things. We can't see displacements if they're smaller than the uncertainty in the topographic measurements. It's quite challenging. And that might be or centimeters to decimeters. Question?
When you're going through your LiDAR data set and you originally are in a vegetated area and you go and make the calculations to remove the vegetation, remove the buildings, and then every level that you go down, you're removing points within each meter block. How do you keep track of your error as you erase layers of the point cloud?
There's multiple errors. There's geometric errors which will stay the same. So where is the point? But you might think of error in classification, right? Like is this point ground or is this point vegetation?
Yeah.
And that is quite tricky. I think the main thing is to not treat some of the classifications as black box. To constantly sort of look at the point cloud, look at the classified point cloud or the derived product like the DEM and say, am I getting what I think or am I throwing too much away?
Okay.
Because some of the settings, Chris will talk about.
I've got a bunch of slides on this.
Okay.
Great question.
Yeah, so let's maybe save it.
Okay.
He'll be able to answer better. So, open topography we'll hear more about. And here's kind of just showing, this is an early picture of some of the data that we had in OpenTopo that were oriented towards faulting. This is mostly the Earthscope data. So there was an effort to scan some of the active faults of Western North America to supplement the seismology and geodetic work that was being done to kind of go to longer time scales. Because we think the landscape records deformation at 100 to 10,000 year time scales, let's say. And this also shows where some of on the map where some of the examples I'll be showing, or I have been showing, come from. So here's the Granite Hills in Arizona. We'll show a little bit from Landers, San Jacinto Fault, Carrizo Plain, Mallorca Cupa, there's Napa, Northern San Andreas.
Do you have Elsinore? I can't tell how far.
Yeah, so, yeah. And Denali I've shown some stuff from. So keep going. We've been really pounding on this, seeing at the appropriate scale point. So here's one thing I thought trying to explain is, so why is it that the shorter your ruler is, the longer the coast of England becomes? Yeah.
Oh, the shortest distance between 2 points is a straight line, right?
Right. So if you make your ruler shorter, then you can measure more distances, right? So this is kind of really associated with sort of used usually for statistical self-similarity or sort of fractal kind of discussion, but it's exactly relevant for our discussion. Like if we want to really finely represent the coast of England, we need a short ruler. Whereas if we don't care about that too much, we don't have resources, we may only have a long ruler, we're not going to quite get what we want. So this ruler length is the analogy for us in high-resolution photography would be the pixel size or the sampling density for our work. Somebody had to raise their hand, I thought maybe. So here's just some ground-based examples, some dense data on the ground, so you really start to see this kind of 3D view of the near surface environment. So here's some of those precariously balanced rocks with the laser scanner there next to them. Here's just this Bemis paper showing structure from motion, so photographically derived 3D models in complex environments. So these are trenches that were photographed. So there you get not only the geometry, but also you get the texture map. So we can see really finely what's on the walls of these trenches. But the key text I have here is we need this ability to sort of have absolute measurement capability sufficient to characterize features and changes in challenging geometric environments. So, if you're flying above someplace, you can only see so much. But sometimes you're down in environments where you need to measure a boulder, or you're in a hole and you need to characterize the trench.
What exactly are you looking at with the PBRs? I know it means that there's minimum ground shaping, but...
Yeah, so we always say there's sort of negative indicators of strong ground motion. So if you still see it, you must not have had a strong enough earthquake in the time that it's been unstable.
Right.
So our work was mostly kind of addressing that last point of how long has it been unstable. So how do these evolve geomorphically? And so, this is this place where there aren't very many active faults in central Arizona. So we tried to say, well, what controls their stability in the absence of significant ground shaking? And basically, the idea is that the granite is kind of fractured, and you have weathering that or alteration that comes down the fractures into these blocks that are fracture bounded, so you end up with these sort of core stones. And so then as the landscape is lowered, you expose the core stones. And then you start to sort of weather the bases of them at a time, then they ultimately fall over. So we were working on characterizing their fragility, so sort of how unstable are they, and how does that evolve?
I have one or two slides on that point.
Okay, so then here's a little bit more on structure for motion application. Ed will talk about this, but here's just a lander's example. We flew a balloon along the surface rupture, but also we had a terrestrial laser scanner there in 2008. And so you can see this, Andrea's question, all these holes in this data are because we couldn't see. They were shadowed from the scanner. So this is accurate data, but here we were in a balloon looking down, and so we could see, sort of differently. And we started trying to do differencing of those two data sets to look at erosion. So here's another point on the scale. So here is a topography at 10 meters per pixel. San Andreas Fault's going through there. Can't see anything. If you go to 25 centimeters per pixel, same place, you see the B4 laser scan, so one of our famous LiDAR data sets for Southern California. All these yellow dots are the ground samples from the laser. We can turn them into a digital elevation model, 25 centimeters per pixel, and get a much richer representation of the topography and even the bushes. This histogram shows the sampling, so about 4 points per square meter. So going to 25 centimeters per pixel is probably sort of pushing it in terms of the resolution. But now we can almost do virtual geomorphology, so we can stand looking this direction at this group that are discussing the offset. So then also we need to be able to measure these landscape characteristics at the appropriate scale. So I showed this already, this drainage network at very fine scales. You see the people here, so you need to have a short enough ruler that we can see the changes and measure the changes in that landscape, as opposed to this kind of more ugly representation from USGS, National Elevation Data Set, which is much coarser and doesn't give us any ability to characterize those fine features. So this is a figure that we put in this Passalacqua et al. Paper, and the idea is so how do you go from kind of the point cloud to the interpretation? And so, and we'll spend some time talking about this over basically all of today, is we have some set of points, but we want to sort of idealize them into, let's say, a surface or some kind of 3D object like this cone. So in this case, we might be looking to find a tree. So how do we find the tree in all the points? And so we can have a sort of a workflow of kind of doing feature identification through sort of processing kind of directly on the cloud, or kind of more idealized features like channel elements, geomorphic rudiments, sediment, vegetating structures. So we come up with kind of continuous fields like that topographic surface, or discrete objects like the tree, or in our case for offset landforms, maybe some channels. And we start to iteratively work on these features, maybe integrate data like from the field or other remote sensing to try to build this kind of near surface model, which is the ensemble of all these things out there, and then start answering questions. And so this is very abstract because we were trying to make it apply to all kinds of things, like sort of ecological questions, geomorphic ones, and faulting related. But I think the point is that most of the time when we talk about DEMs and some of our analyses, we're sort of working down in here, but the data are up here. And so there's a lot of processing. And so in some ways, much of our workshop is about how to give you better ability to interact with the data to kind of answer the question of interest.